Shall we start?
Yeah, sure, please.
So welcome to NCTS number series seminar. So today we are happy to have our speaker, Professor Furusho from Nagoya University, and he is going to talk about p-adic hypergeometric function and related to p-adic multiple polylogarithm. Let's welcome him.
Thank you very much. Thank you. Thank you very much for the invitation. So I'm pretty happy to give a talk here. So my talk, I use this online whiteboard. So maybe it's please check the chat corner. I think Harada-san sent the chat link. That's more convenient. You see here is the chat link. And please access to this chat link so you can see the full view of this board. So you can go scroll and you can change the size freely. So if you are not logging, I think he will send a chat link again, say 5 minutes later on, I hope so. And we don't have PC, maybe ask the neighbors to share the screen. Sorry. So let's start. So what I will talk about the p-adic hypergeometric functions and the p-adic multiple polylogarithm. So what is HG? HG stands for hypergeometric functions. What is this? This is a hypergeometric function. Review alpha, beta, gamma, and G. So this is defined to the infinite summation, starting from 0 to infinity, and this is the Poho-Hammond symbol, beta will n, gamma will n, factorial, G to n. Okay, this is the definition. And so alpha, beta, gamma. And they are complex number with the appropriate conditions. Say, for example, so G is going to be a negative response. It's going to be the integer distance or equal to 0. G is a complex number. Absolute value is more than 1. And say here, so alpha n, this means it's a Poho-Hammond symbol. This is a hypergeometric function. It's quite well known. A multiple polylogarithm. This is a note. L logarithm integral k to k m g. This is infinite summation. The strange way. N1 is smaller than N2, and N2 is smaller than N3, blah, 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 blah. And N1, K1. This is multiple polylog. And because that's when they equal 1, this is polylog. That's an integer polygon. It's a multiple generalizations. I will talk about the p-adic analog of these two functions. Here's a graph. First section, I will call what is known as the complex case. And section 2, I will talk about the p-adic situations. This is a graph. And let me start first section. Hypergeometric function is a solution of hypergeometric Gauss's hypergeometric differential equation. Let me explain. Hypergeometric equation is a differential equation. And gamma minus alpha plus delta plus 1 G. That's a kind of well-known differential equation. The hypergeometric, this is the Gauss's hypergeometric differential equation, and this holds for a function. And that is a function G. First, that is the 2f1 alpha delta gamma Z. Hypergeometric function satisfies this differential equation, which I denote the HG equations. There's a very nice reformulation of this differential equation. Here, let's consider the vector, two-dimensional vector. The second component, so, okay. Consider this two-dimensional vector. Then you can, right? You can change this differential equation this way. This X is a 2 by 2 matrix. I must change the color to minus 1. そこから y。You can reformulate hypergeometric differential equation this way. What is X is 2 by 2 matrix, 0, 0, beta, mu. Y is 0, 0, alpha, mu. What is mu and what is mu? So mu is 1 minus gamma, and mu is alpha plus delta plus. So this is, this is, so this is a reformulation of hypergeometric differential equation. Here, X and Y are 2 by 2 matrix, and G is a vector, two-dimensional vector. This is the formation. And this is very simple, right? So you can check by yourself by hand. This is a hypergeometric equation. So I'd like to emphasize that this is closely related to KG equation. This is KG means what the KG means. KG means there. Yeah, what the KG stands for? This is the alphabet of two versions, KG equations. KG equation means differential equation, which is studied mainly conformal cell. So you consider KG equation. There's a KG equation. And the simplest KG equation is defined as G. Where G, E0, E1. This is a complex number coefficient. Formal power series with two variables with complex number coefficient. This is non-commutative power series. Coefficients. Non-commutative formal power series with coefficient. This is a KG equation, the simplest case of KG equation, which is studied in conformative theory. So here, you have two, I like to write, you have two equations. One is hypergeometric equation, this one. We also have a KG equation, so this one, yeah. Hypergeometric equation and the KG equation, they look very similar. Yeah? There's indeed there's a relationship between HG and KG. You can you can deduce HG from KG. I like this one a lot, but I want to say, if you have a solution of KG equation, if you have a solution of the KG equation, you can construct two solutions. Hypergeometric equations. This is a relationship. You have a solution of KG equation. You can construct a two solutions with hypergeometric techniques and how. Say, let's say E0, E1, C. This is a solution of KG equation solution. Then, if you evaluate E0 to X and E1 to minus Y, then this gives a two solution of hypergeometric equations. G1, G2. Let me explain why. Yeah. You have a X here. This is 1 here. This is E0 here. This is E1 here. Huh? So if you evaluate E0 to X and E1 to minus Y, then it will be a solution of a hypergeometric differential equation. So because this is 2 by 2 matrix, so that means you have two columns. So that you have two solutions of hypergeometric equations. You must be careful. You have to check that each clearly converges, if it converges. We have to check the convergence. Because this is an infinite summation, it might happen that this infinite summation might diverge. But most of the cases, it converges. It was neither some proof, but it is working. This is a relationship of KG equation and the hypergeometric equations. Okay?
So excuse me, can I ask a
Yes.
question? So
Yeah, sure.
when you say the specialization makes sense if it converges. So here you by conversion you mean as long as it converges at some small disk it will be enough, or you have some restriction on the radius of convergence. You need to as large as possible.
That's right.
Just small.
That's right.
Okay.
Yeah.
Okay.
Mm. And what I will talk about is exactly that case. Thank you.
Okay.
Mm.
Thank you.
Well, thank you. So the case which I'm interested in most is solutions constructed by Greenfeld. Greenfeld solutions. There's a solution constructed by Greenfeld. There's a nice solution. Here I denoted KG E0, 1, non-commutative formal power series, and it's a function, complex function, which actually has a following representations. M is bigger than 1, and K1, Kn is an integer bigger than and greater than or equal to 1, and this is a multiple polylogarithms. Here, let me some regularized terms. That's a bit complicated. Some regularized notion of regularization is concerned, but here. To be able to construct some nice solutions of KG equation, which I denote GKG. And one of the important points is that coefficient there appear multiple polylogarithms quite clearly like this. This is a solution. This is a solution of KG equation. That was shown by Dimitrov. That follows from Dimitrov's work. So, if you let's consider the evaluation. Here I say E0 goes to X and E1 goes to -1. Then this will give the two solutions of hypergeometric equations. And what's interesting is that it is shown that actually the 1, 1, 3. This is 1, 1, 2. They are hypergeometric functions. The 1, 2, and 3, it's a differential and multiplied by 0 over beta. There's also another one. So if you consider the derivative solution of hypergeometric equation, the KG equation, and if you consider the evaluation, as a 1, 1 entry, you will recover the hypergeometric functions. This is an interesting observation. And there's a very nice formula which was shown by all. 1, 1 entry is given by. So this is the right hand side, yeah? 1, 1 entry is 2 vector. Well, what is the left hand side? The 1, 1 entry is the left hand side. You see here, X and Y is a matrix which is given by this way. So in principle, it's possible to calculate all the co-entry. And in OI calculated this and shows that we have about OI given by this 1 plus alpha beta. Yes. S G7, okay, and S alpha beta ですね。念のためにもう一回ちょっとり。This is summation. Final summation of multiple polygons. The very last formula is Adonis. Box K on the right is yes. Here again, so I have a thing like this. made with the summation of all the components. And depth is a number of variables. Height is number of components which is bigger than 1. Right? And the case called admissible if and only if the last component is bigger. But here, I think I overextend. This is all the formula. This is a formula how to relate multiple polynomial and hypergeometric functions. Which is a two-way function. This is a hypergeometric function, and the two-way function is Gauss space. And G0KNS, this is a summation of multiple polylogarithms with admissible and weight, depth, height are all fixed. So this is a final summation of multiple polylogarithms. So this is how we can write down hypergeometric function as a infinite summation of multiple polylogarithms. And this is obtained by a relationship between KG equation and the hypergeometric equations. And that's all the first section is about the complex case. Any questions so far?
We have the always formula for any plus one, and so generalized hypergeometric function is in normal set.
Nobody has calculated.
Oh.
But I think it's possible. So we have to find the notions of alternative notions of height and depth. I think. Let's see. Can I go to the p-adic situation section 2? I will go to p-adic situation. Here, say, E is, I don't know, E1, E2. Here it is 0. So my definitions of p-adic hypergeometric function, or let's say it's a formal value version. It's a formal positive version. P-adic hypergeometric function is fine. 1. There is A, B, C, C. This was the same formula. But the same formula, so. E plus B and what is Coulomb function. I have to explain it more. A P. Okay. This is a normal C, where this is my definition of the formal version of p-adic hypergeometric functions. Where we call this is a set of p-adic formal functions, p-adic formals, related integrals. And in my setting, this is equal to the function generated by Cp and p-adic logarithm and p-adic multiple polylogarithms. This is the p-adic analyzing multiple polylogarithms, which was introduced by myself. And this is p-adic logarithm. P-adic logarithm. The p-adic function group locally analyzed group homomorphism from C multiplicative group of Cp to additive group of Cp. And this function is unique once we fix a branch. P-adic logarithm. This is my definition. The first version is a formal power series version of p-adic hypergeometric function. This is commutative formal power series with three variables A, B, and one G, and the G0. G0P is defined in the same way as the summation of p-adic multiple polylogarithms. This is my definition of the formal version of the p-adic hypergeometric functions. And now I'm going to my main result. But I have shown this kind of specifications for convergence. Let's choose the branch of p-adic logarithm to be a Cp and assume that's a very technical condition alpha, beta, gamma is the element of P. It's a localization. It is just a it's a rational number, which is divisible by P. And with gamma. Gamma is not negative integer or zero, and alpha plus beta minus gamma, alpha minus beta, they are not there. And also, it is not positive negative. Under that condition, we can show that actually, then the formal version of my p-adic hypergeometric function A, B, C, alpha, beta, gamma. This always converges under that condition. And give some up. To F1 alpha, beta, gamma. QP minus 1. So, my definition of p-adic hypergeometric function, the formal version is the formal power series. But if you evaluate the alpha, beta, gamma this way, yeah, it's that satisfies that assumption. This always converges for any g, which is as the element of QP other than 1, it always converges. So it is a map from QP minus 1 to. This is my first result. My second result is that, especially when G is p-adic offset value is smaller than 1, so in that case, it agrees with the usual power series expansion. So, I think my function is a kind of natural extension of the function of power series, which converges into the open units. It's a kind of analytic extension of the hypergeometric function. The last problem, everyone. So there's a theorem. I think it is due to Gauss. It is a relationship of a hypergeometric function and gamma functions. You consider the limit goes to 1. Okay. My function is not determined at the point 1, but if you consider the limit, you can show that it actually infinite direction. Complicated problem in itself. For instance, this p-adic function, gamma function, this is the function studied by Yasuno. This is my result. So it's a short. So, okay. So my function, hypergeometric function, this is the formal version of p-adic hypergeometric function, which is defined by this the power series with three variables. But if under this condition assumptions, you can consider substitution evaluation, and we can show that this converges, and it is a map from QP minus 1 to QP, well-defined map. And especially if you consider the open unit centered at origin, it agrees with usual power series expansion. And if you consider the limit value to the point 1, which is not determined, but the limit is given by the product of the infinite product of gamma function. This is myself. So it's a kind of a p-adic analog of Gauss say. This is my technical. Just let me go back to the user case, we call that. So I have to briefly recall. Compress this. The compress this. So, it's different. Let's looks. Denominator and numerator opposite plus. This is complex case. So this is p-adic analog.
I have a question.
Yes.
In the first formula,
Yes.
do you need to pick up when z approach to 1? It doesn't depend on the way to change.
So actually, that's a quite delicate point. But here, I'm saying this is an element of QP, right? If we consider the extension of field, then we have to talk about it. That's why I restrict to QP. Actually, my result is more general. So yeah, we can consider the bigger extension field, but we have to, how to say, restrict some absolute ramification index to make converges. But at least if we walk over QP, then we don't need to care that. Yeah, thank you. So that's why the short version. If it is technical, it's more. Yes.
For the p-adic gamma value with the third formula, the specialization has rational number.
Specialization.
What gamma p evaluates those numbers? Are they proper operation?
You mean that this infinite product is this?
For each specialization, gamma p at 1 plus pk mu plus alpha.
Because I'm saying the mu and alpha beta are rational number. But I don't know. Yeah.
But it can be proper fraction. Can be proper fractions, right?
Proper fraction.
Rational number, but not integers.
Rational number. But so are you talking about this gamma value? Mu
The
plus alpha.
specialization at those points. Yeah.
Points.
Yeah.
So
It's kind of point.
yeah, I'm saying that this is rational number. So yes, it's a rational number.
Rational number.
So what happened to this number? So I don't know. I think is there any work on this? I can't. I don't know. Yeah, that's interesting because it is such a student of the national numbers. I have to start with some start with that. So it's so have Right now, I can just say I don't know. Yeah, I should research. I should search for this. Sorry. The proof is down. Decision-wise, like verifications. Decision-wise, check each decision in the tubular neighborhood of 0. So this means the Z reduction is inverse. Here, this is the tubular neighborhood. It's an notation. This is the geometry. You can show that in the level formal power series, A, B, C, A, B, C is the formal power series. It's a generator the formal power series. This is just a polynomial. This is a rational. Yes.
You need to see, right? You do see.
Yes, sorry. Oh. This is a formal power series with rational function coefficient with 3 variables. You can show that this is what the holds. So it always come at the right hand side. It always converges. Well, A, B, C is equal to out. Now, this outbound frequency element of CP. If gamma is rational, we can show that this converges. So this is the argument in residue plus of 0. Next written whatever. Other residue, kusai, here. Kusai is a use of the Here we use the extension of formal p-adic multiple polylogarithms. Just Taylor expansion. We have this Taylor expansion at the center of the design. P-adic multiple polylogarithm. If you take a differential of p-adic multiple polylogarithm, it is again a p-adic multiple polylogarithm multiplied by 1 over g and 1 over 1 minus g. So it roughly says a p-adic multiple polylogarithm closed under the differential. And what's important is that you can show that this below belongs to the PD ideal rate K, sorry, K minus I. This is a result shown by Kajismachi. Kajismachi is another guy who works on another one of the people who works on p-adic multiple polylogarithm and what's the result about this. This result was shown by Kajismachi. This is PD ideal. PD, what's PD ideal? Let me briefly explain. So PD is called divided power equal PD ideal. Such that the differential of p-adic multiple polylogarithm attributes of unity, then it belongs to the power of PD ideal. This is the result that shown by Kajismachi group line. This is submodule generated by this one. This again. By using this, and by using Kajismachi's result, we can show the conversion. We can check the conversions. Actually, first one, A, B, B, C. And we consider the restriction to that. Belongs to that. Cycle of extension A, B, U. So U, C is equal 1 minus C. This is the first. When alpha, beta, gamma, or just a p-adic integers, we don't need to say it is rational number. We can show that 2f from p, alpha, beta, gamma, z converge. It's not the unit list, but the largest convergence is a bit smaller. Yes. If you say all the rational, in that case, you can show that this converges. Open units. This is my argument. So the roots, the residue of roots of unity, we don't need to assume so alpha beta gamma is rational. We just say it's enough to say that gamma is element of GP. But the largest convergence is a bit smaller. It's not so cover the full full disk. But we usually restrict alpha beta to gamma to the element G times C. The rationale is in that case, the measures it converges the full disk. So at least in the disk disk, there's a unit. So we can relax the condition to show convergence. My next one is not equals to 1, but infinity. Here, I'm using some techniques of functional equation of multiple polylogarithms. There is some functional equation between multiple polylogarithms G and 1 of U. That can be proven by using symmetry of multiple phase equations. We can show that two kind of relations of it's not a function. And G minus A is defined to exponential minus A. A is as a formal variable and the p-adic logarithm. And G minus B shall minus B. So G. So we can show kind of a relations. It's a kind of symmetry of formal version of p-adic hypergeometric function.
So the exponential is the p-adic exponential.
The exponential, no, okay. This is an element of QP. It's not a p-adic, just a formal expansion. Because here, okay, this is a formal variable. Yeah, the constant, once we have a constant term 0, if we have a constant term 0, then we can take an exponential because this is a formal power series. So just summation. So we can prove this. We can calculate just using the function equations. We can prove this. And from which we can reduce the local behavior around infinity to the local behavior around 0. And from which we can prove that C is equal given by QE this one variable polynomial algebra A, B, U, and 1 over 0. So p-adic has a geometric function and it's reduced to infinity.
Is it p-adic?
So it's p-adic, yes, yes. So here, if we consider the p-adic logarithm, we have to fix a branch of p-adic logarithm. So here, if you choose p-adic log, branch of a p-adic log to the pth integer, and if you say let small generous he asks if we take k to the field extension of QP, whose absolute ramification index is smaller than p minus 1, and let's say G is the element of K, and further, let alpha, beta, gamma minus 1 is element PGP with alpha minus beta difference belongs to, but not. Then, this periodic hypergeometric function always converges when this is what I have shown. The local behaviors are on infinity. So few more. So the condition, you have a several condition, but let me explain how they contribute. So choose the repeat two conditions. These two conditions. This is necessary to show the convergence of these two exponential. That's why we choose conditions. This is an infinite summation. There's an infinite summation. If you say log p is GP, if you fix the absolute ramification index more than p minus 1. So this k can be an infinite extension. Absolute ramification should be smaller than p minus 1. If you say alpha and beta to PGP, then in that case, you can show that this to evaluate A, B, alpha, beta, then you can also show that under this condition, it converges, always converges. That's the condition I required. And also, the two conditions. These two conditions is required to prove that convergence of these two things. That's how these two conditions are required. So under this condition, this function always converges as a neighborhood of infinity. Go to the neighborhood of 1. In the last few minutes. In the neighborhood of 1, the argument is kind of similar argument by using the function equation. We have a function equation of p-adic multiple polylogarithm. We have F1, A, B, C. There is argument to define what does it mean, but so let me skip. The kind of similar argument, but I have to use some more. by similar argument, we can get a kind of symmetry of periodic multiple periodic hypergeometric functions. And by the same argument, under the same condition, is can show that the 2F1 also converges. How I check that in the residue at the point 1, at the residue class, at the local neighborhood at the point 1. And how the periodic hypergeometric equation is obtained like this. If you consider G equal 1, but you have to consider the specific dicet. G belongs to some field whose absolute ramification index is smaller than p minus 1. If we consider in such a case, A, B, C, Z, then this can be calculated to equal to S1. Because here S2, here because S2, if you consider G equals to 1, because of this is always 0. And this is the point 1. So the value, there's no dependency of G. So if you consider that G equals to 1, this value is 5. This is S1. And here, the next, so I have to skip that. So here we have to use some kind of using periodic associators. If you evaluate some specific 2x2 matrix to associate x and minus y, then you will recover the gamma functions. There's some argument using this argument to associate that. So I can't talk a lot. If you consider the associator, you can show that this is by for which we can deduce the validity of periodic hypergeometric functions. So, sorry, that's it. So, this is my definitions of associated periodic hypergeometric functions. Yeah, so perhaps I should comment. So, there's another approach by Benedict Dubourg. He has also introduced a periodic hypergeometric function, which is a totally different way. So I don't know how my definition of periodic hypergeometric functions are related to his function. So far, I have no idea. So my approach is to use periodic multiple polylogs, so it's totally different from which box. So that's it. Sorry, 5 minutes. Wow. Thank you very much.
So are there any questions or comments?
So yeah,
Yeah,
can I ask question?
Yes, sure.
Yeah.
please.
So you're in the brief version of your theorem, you define the periodic hypergeometric function. So I'm wondering if this, because your motivation begin with some solution of certain differential equations. So what's the connection with your p-adic hypergeometric functions with the differential equations.
So, thank you very much. Yeah, I should mention it. So, my p-adic hypergeometric function also satisfies this differential equation.
Yeah.
Yeah.
Okay, edge break.
So,
Okay, okay, I see.
Yeah, so it's a formal argument. So it's a, it's enough that it's a solution of this equation by construction.
And also, so you can define some kind of specialization map from this this string fields solution to your p-adic one.
Yeah. There's a
Because the complex
solution.
one is the evaluation at some special point, right? You evaluate E0, E1 at some special point.
Yeah, that's right. That's right. So the Greenfield works on only in complex case. And there's a solution of p-adic KG equation. And
Oh,
that's
okay.
actually, that was constructed by myself. And
Okay.
so if you and you can consider the evaluations and yeah.
Then you can recover the p-adic hypergeometric function here. Okay.
Yes.
Okay.
But so everything you have to be careful. You have to check the conversion. You have to verify the
I see.
conversions. And that's what I did.
I see. Okay. Then I also have a question. What's the so if you change the branch of your logarithm, how your solutions change? How does it change? How does this so for example, is your p-adic hypergeometric does your p-adic hypergeometric function depend on your branch of p-adic logarithm choice?
That's right. That's right. In the local neighborhood of infinity and 1, it depends on the choice of branch.
The p-adic logarithm.
But
Right.
Other place, it is free from the choice of branches. Right.
So is it possible to describe the relation between two different hypergeometric functions with respect to different choice of p-adic?
Different choice. So in principle, yes, it is.
Oh, but it may be okay because your common integral also depends on choice. So okay, I see.
Yeah, because multiple polylogarithm, if we change
Depends
the
on-
branch,
Right.
then
Okay.
the values, and it's possible to.
But it may be okay. Yeah. Okay. I see. In principle, yes. Okay.
Yes.
I see. Okay. Thank you very much. Thank you.
Thank you. Thank you for this one.
So I have a question. So in a complex case, some special values of hypergeometric functions occur as periods of CMA curves.
The periods of CMA ellipse curves.
I'm wondering, can you say or provide any examples of some geometric meaning of your of the special values?
The bulk of the p-adic hypergeometric functions related to such topics.
Oh, you mean the work?
Duboc. Benedict Duboc. So, but mine, so far, it's P1 minus 3 points. So, anyway, I don't know. Perhaps I have to relate to the Dubroc's p-adic hypergeometric function. That's what I have to do.
So his special values are related to some p-adic period or
some p-adic periods.
Or some special value of p-adic function, something like that. Yeah. Like LE2.
So, maybe right. I have to say, yes, in short. So,
So any other questions?
Any of this term does not appear in the case of the log p-adic hypergeometric function. This is so all of them are new
So, what was that? Yeah, so the box p-adic hypergeometric function is not defined in the full space. So, for example, it is not defined in the neighborhood of infinity, and even so, the box case. So, even so, for specific result, not all result, not some specific, maybe half of them. So, he gave analytical continuation, not the whole space of OCP. So, but the result is really deep. So, on the other hand, so I have a analytical the kind of prolongation by using the prolongation of multiple polylogarithms. So, Oh, okay. So yeah, the methods are totally different.
Thank you.
So any further questions or comments? So if there are no further questions, let's thank the speaker again.
Okay.